That's pretty awesome. Okay. All right, you know we're always talking about important graphs in every unit. So in this unit, the most important graph for us to analyze is a force time graph. And so time on the x and force on the y. And usually we're talking about really short time periods, like the plunger in the cart example where the plunger pushes the two carts apart, or a ball hitting a wall. The force between the ball and the wall is going to be very, very short. All right? And in a collision, what actually happens, on first contact, the force is 0, and then the force increases as the ball kind of acts like a spring. So this is when the ball is, like a tennis ball, is most compressed against the wall. And then the ball pushes off, and you get something like that. Okay, now in the real world, that could be a curved graph, either concave or convex. All right, we don't really care. Calculus would help us with those curved graphs, okay, but we don't really have to do that. If you guys get a graph, it'll be some kind of geometric shape that you can calculate the area of, okay, because that's what we care about with these graphs, is the area. Okay. Anytime we analyze the area of any graph, it's easiest just to take a square snapshot and think about what it means. Okay, so the area of this is equal to base times height. Okay, what's the base measured in?
Time.
Yep, time, seconds. And what's the height measured in? Force, newtons. So we got a time times a force. That looks suspiciously like what? FT, time force. What is that? FaceTime. Wow. Okay. Wow. Okay. Force times a time is a delta P. Okay? So in other words, what we need to know is that the area under a force time graph will give us impulse. Okay, that's going to give us impulse. And an alternative unit for impulse is Newton seconds, by the way. You'll see that come up every once in a while. If you see Newton seconds, it's the same as kilograms times meters per second. Okay, that'll show up here and there, these graphs. Okay, and what we could do with that, for example, is we might take our force time just by getting the area, because the force is changing is the complicated thing here. It's not a constant force. So we can take this area, plug it in for this value, and we might set that equal to m delta v. And from that, we might be able to find the change in speed of the object. Okay, that's one example. Or if we knew the change in speed, we might be able to figure out the mass of the object. All right, let's do an impulse problem, for example, here. All right, calculate the impulse experienced when a 70 kilogram person lands on firm ground after jumping from a height of 3 meters. Okay, when you jump off a rock or something like that, okay, do you like lock your knees out and land like a stick?
I hope not.
No, you bend your knees like that, increasing the time and decreasing what? If you increase this, you're going to decrease that. Okay, that's why you have it programmed in your heads to land by bending your knees. Okay, because you guys already know physics. Easy. Done. Okay. So think about that next time you jump off something. Alright, so we need to calculate the impulse. To get this, we can either know force and time, or mass and delta v. Which route should we go this time? We're going to go m delta v. We don't know anything about the time, the impact time here. Okay? Although there is actually a way we could use this, but we don't need to talk about that right now. Okay, now we've got the mass. How are we going to find the change in velocity? Find the speed they hit with. Okay, they're jumping from a height starting at 0 speed. And we can do this two ways. We can do this using kinematics or energy conservation. So let's put both equations, but we'll only use one. If we want to go kinematics, we do Vf squared equals Vi squared plus 2a delta y. That equation is nice because there's no time in that equation. Okay, so just a little review of kinematics. The other way we can do it is energy conservation. We can say EI equals EF. Okay, initial, we've got potential, and right before they hit, we got kinetic. Okay, so the mass actually cancels. This is going to be the speed they hit the ground with. And yes, that speed is going to 0 during the impact portion too. If we rearrange for it, we get velocity is equal to square root of 2gh. That's just multiplying the half by 2 on each side and square rooting. Okay, so let's plug in some numbers here. Square root of 2 times 9.8 times 3. Okay. And if we punch that into our calculators, that is going to give us a 7.7 meters per second. Okay, now we want the impulse for the landing on the ground portion. Okay, so this is their speed they hit with. Okay, what's their final speed? 0. Alright, so we're going to do delta P is equal to m delta V. And we'll just plug in some numbers. So we've got a mass of 70. Okay, now the signs get a little weird here. Okay, we call the down direction negative most of the time. So I'm going to go over here and put a negative sign on that. They're going down to start. Okay, their final velocity is 0. When we do a delta, we do final minus initial. So I'm doing a 0 minus a negative 7.7, which is going to turn that into a positive. Okay, so let's plug that in real quick before the bell rings. Okay, this is going to come out what sign here? Positive. So really I'm just doing 70 times 7.7 when it comes down to it. And I get positive 539. So my impulse is equal to positive 539. Okay, what unit should we tack on there? Okay, we got kilograms times meters per second. No shorthand to the momentum unit. Okay, questions on that? Okay, typical impulse problem. Alright, there's a UT that kind of uses some of that stuff. Alright, let me know if you have questions on it.